Okay, so in chapter 3, we start with section B, um, and we're going to be talking about numbers in the real world. And particularly, we're going to be really discussing how to put numbers in perspective. So one of the things that we really delve into is scientific notation, and because that gives a way to put very large numbers in perspective. Scientific notation is a format in which a number is expressed as a number between 1 and 10, and that's important that the number is between 1 and 10, and it's multiplied by a power of 10. So here's some examples. Okay, we've got 6,700,000,000. In scientific notation, it can be very confusing to see all of those zeros and to have to count. Now, the commas kind of help us organize that. But if we're trying to type that in the calculator, it's going to be difficult to get the exact amount of zeros without having to go back and look and check and make sure that you did the exact thing. So sometimes we change it to scientific notation. So 6,700,000,000 turns into 6.7 times 10 to the 9th. Now, if you look at this, we know that the decimal place would be right after this zero. So if we moved it back 1, 2, 3, 4, 5, 6, 7, 8, 9 places, so we know that 6.7 is between 1 and 10. So that's the number that we want in the front. And because we moved it 9 spaces, that's where we come up with 10 to the 9th. Okay, on this one, it would be very difficult to type this in the calculator. So I'm at 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 to make that a 2. And this is a very, very small number, and so it's going to be to the negative power because we're going the opposite direction when we move it, so 10 to the negative 15th. Perspective through estimation. An order of magnitude estimate specifies a broad range of values, usually within 1 or 2 powers of 10, such as 1 in 10,000s or 1 in millions. Here's an example. It's the total annual ice cream spending in the United States measured in thousands of dollars, millions of dollars, or billions of dollars. Well, reasonably, we can guess that an average person has something like 50 servings of ice cream per year. So if we talk about the spending, average person has 50 servings per year. And let's say a serving costs $1 a piece, so $1 a serving, times, and where are we coming up with 3 times 10 to the 8th? That is an estimation of how many people are in the United States. And so if you multiply 50 times 1 times 3 times 10 to the 8th, you would get 1.5 times 10 to the 10th every year, which is 1.5 billion per year. And our calculators will do this for us. Okay, if you just type in 1.5 times 10 to the 10th power, your calculator will handle that for you. If you want to do it by hand, you would take 1.5, and because this is raised to the 10th, we'd have to move it 10 times. So 1, 2, 3. We'd add zeros. 4, 5, 6, 7, 8, 9, and then we would get to 10. Okay, if we go back, we've got, and that ends up being 15 billion after we combine our commas. So a lot of times we use scientific notation in everyday uses in language. So energy released by metabolism of one average candy bar, 1 times 10 to the 6th power. So these are in joules. Energy needed for 1 hour of running, 4 times 10 to the 6. And it gives you a lot of examples. Energy consumption, would hate to have to write all 20 of those zeros if we had to write it out by hand. I would especially hate to have to write all 34 of those zeros. So annual energy generation of the sun, that's huge. And so there's sometimes when it's just better to use scientific notation because it helps you to be able to not get confused whenever you're writing that number and having to list out all of those zeros. So compare the U.S. population to the world population and the U.S. energy consumption to the world energy consumption. What does this tell you about energy usage by Americans? Well, the world population is about 7 billion. 7 billion, if we were to write that out, we would have 7 with 9 zeros behind it, 7 billion. And that's why it's 7 times 10 to the 9th. The U.S. population is 300 million. So if we want to write 300 million, we'd say 300, and the million would be 6 zeros behind it. If you'll look, we've got 8 zeros, so 10 to the 8th. So if we're comparing the U.S. population to the world, we would take our U.S. 3 times 10 to the 8th, divided by our world, which is 7 times 10 to the 9th. And look what they've done. They've combined this first number and said, well, that's going to be 3 over 7. And how did they come up with this 10 to the negative 1? Well, when you're dividing exponents, these have the same base because they're both 10s. The base is 10 to this exponent. So when you're combining those and you're dividing, the rule is that you can subtract them. So 10 to the 8 minus 9 gives us 10 to the negative 1. And if we simplify that, 3/7 times 10 to the negative 1, we would get this. This is not in scientific notation, right? It's just, and they have rounded this number because we've got a congruent sign right here. So if we were going to compare the U.S. population to the world population, we would make a fraction, and then we would simplify that fraction. The U.S. population is only about 4% of the world's population. But as shown in Table 3.1, in the United States, that was that table we were talking about, the joules. The United States uses about 1 per 5.7, or 18% of the world's energy. So 1 divided by 5.7 is going to give you rounded 18% of the world's energy. That is, Americans use more than 4 times as much energy per person as the world average. So let's talk about perspective through scaling. So we've got a map here, and 1 centimeter on our map is going to be equal to 1 kilometer. So you can look down here and they've got this marked off. So from here to here is about 1 kilometer. That would be 1 centimeter. So this would be 2 centimeters, 3 centimeters, and so on and so forth. So here's what it looks like graphically. As a ratio, 1 centimeters is equal to 1 kilometers means a scale ratio of 1 to 100,000. Okay. So let's talk about that really quick. A centimeter, so if we talk about a meter, which would be our base unit, there are 100 centimeters in a meter. Okay. There are 1,000 meters in 1 kilometer. So we've got 2 decimal places here, right? We've got 2 zeros to get to meters, and then to get back to kilometers, we've got 3 zeros. So that's how they're coming up with this 2 zeros and these 3 zeros, 100,000 right here. The distance from the Earth to the Sun is about 150 million kilometers. The diameter of the Sun is about 1.4 million kilometers. And the equatorial diameter of the Earth is about 12,760 kilometers. Put these numbers in perspective by using a scale model of the solar system with a 1 to 10 billion scale. Okay, so we're going to talk about the scaled Earth to the Sun's distance. So what we would want to have is the actual distance divided by 10 to the 10th. And the reason that we want 10 to the 10th is that 10 to the 10th is 10 billion. So if we wrote down 10 with 10 right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 zeros gives us this 10. So 10 to the 10th. Okay, and so they've got the actual distance divided by 10 to the 10th power. And it says the distance from the Earth to Sun up here is 150 million kilometers. And so this is where they're coming up with the 1.5 times 10 to the 8th. If we wrote down that number, 150 million, this is what the number would look like. Okay, so if we start talking about moving our decimal so that it's 1.5 times 10 to the power, right? We'd have to move our decimal 1, 2, 3, 4, 5, 6, 7, 8 places. And that's how they're coming up with this 1.5 times 10 to the 8th divided by 10 to the 10th power. Okay, so 1.5 times, and remember that trick we did before, where these bases are, these are both 10 raised to a power. So 10 to the 8th and 10 to the 10th, 8 minus 10 is going to give you -2. So that's how they've reduced this. Now, where did they come up with this 10 to the 3rd meters per kilometer? Okay, and remember we talked about how a meter, so 1 meter is equal to, actually, 1,000 meters is equal to 1 kilometer. Okay, and so this number right here is 10 to the 3rd because we've got 3 zeros. So 10 to the 3rd meters per 1 kilometer. And so they've taken these things and they've multiplied them out. So they multiplied this times this, and they're coming up with 15 meters. The kilometers cancel out, and so our units are just 15 meters. Note that in the last step, we converted the distance from kilometers to meters because it's easier to understand 15 meters than 0.015 kilometers. We can find the scale Sun and Earth diameters similarly, this time converting the units to centimeters and millimeters, respectively. So if we've got the scale Sun diameter, we want the actual Sun diameter divided by 10 to the 10th. And so 1.4 times 10 to the 6th would be the actual Sun's diameter. And then we've got, we moved our 1.4 down, and then they've got bases that are the same. And so 6 take away 10 is going to be 10 to the -4th kilometers. And then this number right here, we're comparing centimeters to kilometers. Remember, there's 100 centimeters in 1 meter. There's 1,000 meters in 1 kilometer. And so that's where they're getting their 5 zeros, 10 to the 5th centimeters per kilometer. So they've multiplied this and this. The kilometers canceled out, and they're left with centimeters. The scale Earth diameter is equal to the actual Earth diameter divided by 10 to the 10th power. So we've got the actual Earth diameter of 1.276 times 10 to the 4th kilometers divided by 10 to the 10th power. Okay, and now we're going from millimeters to kilometers now. Okay, and millimeters is, there is 1,000 millimeters in 1 meter. There is 1,000 meters in 1 kilometer. Okay, so we've got these 3 zeros and these 3 zeros, and that's going to be how you get the 6 right here. Kilometers are going to cancel out. You're going to do 1.276 times 10 to the negative 6 times 10 to the 6. Now look how that worked. This time we were not dividing the bases. We were multiplying them, and they both have the same base. So instead of subtracting the exponents, when you multiply them, you add them to get rid of them. Your calculator will do this for you, but I just wanted to point that out. So 10 to the negative 6 plus 6 is 10 to the 0, which is just 1. And so 1.26 times 1 just got us back 1.26. The model sun at 14 centimeters in diameter is roughly the size of a grapefruit. The model Earth at about 1.3 millimeters in diameter is about the size of the ballpoint in a pen, and the distance between them is 15 meters. Okay, and we got this information from those 3 calculations we just did. So one way to put $1 billion in perspective is to ask a question like, how many people can you employ with $1 billion per year? Let's suppose that employees receive a fairly high average salary of $100,000, and it costs a business an additional $100,000 per year in overhead for each employee's, the cost for the office space, the computer services, health insurance, and other benefits. So the total cost of an employee is $200,000. So $1 billion would allow a business to hire, okay, so we've got $1 billion. We're going to spend $200,000 per employee. So if we change this to scientific notation, right, 1 billion, remember a billion has 9 zeros, so that's how they've turned it into this. 200,000, if we move our decimal 5 times, we'll have the 2 between 1 and 10 like it's supposed to be, and we moved it 5 times, so that's 10 to the 5th. Okay, and so now we can do 10 to the 9th divided by 2 times 10 to the 5th. You would want to, if you're typing this in the calculator, it would probably be best to do 10 to the 9th in parentheses divided by, to make sure you're dividing by this whole thing, 2 times 10 to the 5th. Okay, and the calculator would probably give you the answer 5,000, which is 5 times 10 to the 3rd, right? If we move our decimal 3 times, okay, which is what we've got here. So 5,000 employees. If we had $1 billion a year and we spent $200,000 on their salary and expenses. Another way to put $1 billion in perspective also points out how different numbers can be, even when they sound similar, like million, billion, and trillion. Suppose you become a sports star and earn a salary of $1 million per year. How long will it take you to earn $1 billion? Well, we simply need to divide 1 billion by your salary of 1 million. So we've got $1 billion, which is 10 to the 9th, divided by 1 million, which is 10 to the 6th, which is 10 to the 3rd years, which is 1,000 years, right? So that's kind of crazy. You think $1 million is a lot of money if they're earning $1 million a year, but it's going to take them 1,000 years to make $1 billion. Even at a salary of $1 million per year, earning $1 billion would take 1,000 years. Crazy.